Okay, looking at these systems of equations, before we get into the mechanics of actually finding solutions, I want to think about solutions by investigation. Like just, high bird's eye view looking at these equations, what can we say about them? Um, Now, a lot of times people get confused about this. What is 2x plus 3y? Well, I want you to just kind of think of this as a blob. This is a blob right here. This is something is equal to 6, right? Something over here is equal to 6. Well, that thing has a value of 6, right? That's what an equation means. These two things are equivalent to each other. Just like with our x plus y equals 10, right? Um, these two numbers, like 6 and 4, they have a value of 10, which is equal to 10, right? Or 5 and 5 have a value of 10, which is equal to 10. So this is just some number right here. It's some blob that is just a placeholder for something that has a value of 6. So if that same blob is right here, we can say, well, this blob should be equal to 6, but it says this blob is equal to 10. So is that possible? Actually, no, it's not, right? Because 6 is not equal to 10. You know, I can replace this with 6. And if I replace this with 6, I have 6 equals 10, and these things are not equal. So um, you can look at this, and before even doing any kind of math, you can straight off say there is no solution for these variables that would make both this blob equal 6 and this blob equal 10. Right? So this is a case where there's no solution. And this comes from like our rope example that we did on the first day. When we have a rope that has the same thickness, right, and they're two different lengths, if I were to tie a knot in that one and a knot in that one, well, it reduces by the same amount. So these two ropes are never going to be the same length, right? So that's this kind of situation because the rate of the change is the same. And if you look at this graph right here, or these two equations right here, we know that this is a linear relationship and that the rate of change is 1/2. So each time um, this number is going to increase by 1/2 and it's starting at 2, right? So the starting point is 2. This one's increasing by 1/2 every time that we go up by 1 in x, and it's starting at -3. So this, we know from graphing that it's going to have a slope of 1/2 and a y-intercept of -3, and this is going to have a slope of 1/2 and a y-intercept of 2, and they're going to be parallel lines that have the same rate of change throughout, so they will never cross and they never have an intersection point. So there's two ways to notice that something has no solution. If they have the same slope, same rate of change, there's no solution because they are parallel lines when graphed in the xy plane. Or they have no solution when you can just recognize that this equation is equal to two different things. Okay, and you could rearrange this equation to make it look like this. I could subtract 1/2 x from both sides, and then I have 1/2 x plus y is equal to 2, and 1/2 x plus y is equal to -3. So that blob would not be equal to 2 and -3 at the same time. Okay, so that's no solution. Um, Here's another example where these are just, so I have 2x plus 3y is equal to 6, and 4x plus 6y is equal to 12. This is a little bit tricky, and what's happening here is we have this equation that's just off by a factor. If I divided both sides by 2, all right, this would be 2x plus 3y is equal to 6, right? So I could recognize that this blob is equal to 6, and then this blob is also equal to 6 here. So it's not really telling me any new information. All it's saying is the same exact thing. So this, if I were to graph this line, it would be something like this. Let's see, when x is equal to 0, y is equal to 2. And when y is equal to 0, x is equal to 3. 2x equals 6 means x equals 3. So the line looks like this. And then multiplying it by 2 doesn't really change anything. So here, if I said x is equal to 0, still y is equal to 2. And when y is equal to 0, I get x is equal to 3. So 4x equals 12 says x is equal to 3. So it has the same line right on top of the other line. And so this is an infinite number of solutions. It's just like when you have, when we solved our equations and we had 0 equals 0, that means there's an infinite number of solutions for x. So it's kind of like, well, this is equal to 6 and this is equal to 6, so I could throw them equal to each other. So 2x plus 3y is equal to 2x plus 3y. And really there's an infinite number of solutions that would make that true. And the same thing happens here if we were to solve for y and put it in our nice little y equals mx plus b form. If we were to solve this one, also add 3/4 x to both sides, we see we get the same equation. And the slopes are the same, just like in our example with no solution, so the lines are parallel, but they also have the same y-intercept. So in this case, the y-intercept is 2, and the slope is 3/4, so of 3 over 4. And it's just the same line on top of itself. So this is another case of infinite solutions. So you first check to see if the slopes are the same. If the slopes are the same and the y-intercept is the same, then it's the same line, right? If the slopes are the same and the y-intercept is different, somewhere like that, then the lines are parallel. There's no solution. Okay, so that's just a way to investigate and determine if something has a no solution or infinite solution. Now, if they have different slopes, if it was just one was slightly different, it would have an intersection somewhere, right? So then it would have at least one solution. And this is the example with a rope, before I get to one solution. If we had two lengths of rope that were the same, they're already equal to each other. And then if I were to tie a knot in both of them, they would still have the same length. And tie 2 knots, it'd still be the same, and 3 knots, and so on. So this is infinite number of solutions, and that's the thinking about the rope example, that they get shorter by the same amount each time. So the rates of change are the same. Now, finally, to recognize if something has one solution, you reduce it as much as possible, and if they're completely different types of equation, that means they're two different lines with different rates of change. So I don't know what the graphs of these would look like, but there would be some intersection point somewhere, and that would be one solution. You could never have, if you think about it, if they're off just by a little bit, two lines, if they're off just by a little bit, there's going to be an intersection somewhere, right? And it's going to be out there. If they're off by a little bit, I don't know, that way, just a little bit, I can tell that they're going to intersect somewhere out there, right? So there's going to be one solution. Now, you can't put these lines in any way where there would be, more than where they would cross the other line twice, right? So lines are very, rigid, and they only have one intersection point. So there is either no solution, infinite number of solutions, or one solution. We're going to get into how do we find that one solution in the next part. But I just want to bring this up so that you know that by investigation you can tell how many solutions there are. This last one, you can see there are different rates of change. So this one's increasing by 1/4 each time. This one's increasing by 5 each time. So this one's easy enough to graph. Intercept is -3. The slope is 1/4, so up 1/4. And this one, the intercept is 4, so something like that, and the rate of change is 5, so it's a pretty steep line. It's going to be something like this, and it's going to be something like this. So I expect that the solution would be somewhere in the third quadrant. Okay? Oh, and this is the example of when we have two different thicknesses of rope, so it's going to be a different rate of change. So maybe this one's thicker. And when I tie knots in it, there is some point where they're going to be the same. And you might have to kind of think about, well, maybe there's like negative knots or something like that, because maybe the solution is like, you have to kind of think outside the box here and think that, if you had a thicker piece of rope that was already shorter, you know, negative knots might like add length to it or something like that. So anyway, that's a way to think about these.